Everyone knows about the legendary locomotives that conquered mountains and hauled impossible loads across continents. But almost nobody knows about the machines so powerful they literally changed the shape of the ground beneath them. In the 1940s, railroad engineers discovered something troubling on certain mainline routes. Perfectly straight tracks were developing gentle curves where none had existed before. The steel itself was bending, not from age, not from wear, but from raw, concentrated force passing over it again and again. The culprit wasn't a flaw in metallurgy or a mistake in construction. It was a locomotive doing exactly what it was designed to do: deliver so much power to the rails that physics itself started to give way. The Chesapeake and Ohio Railway's massive articulated locomotives, particularly their H8 class Alleghenies, represented the absolute peak of steam power in America. Built by Lima Locomotive Works between 1941 and 1948, these machines weren't just large. They were instruments of controlled violence against everything that stood between them and the movement of coal. Each Allegheny stretched nearly 126 feet from coupler to tender, weighed over 770,000 pounds fully loaded, and could develop 7,498 horsepower at the rail. That number demands pause. In an era when most locomotives struggled to exceed 5,000 horsepower, the Allegheny was generating power equivalent to 75 modern automobiles, all channeled through 8 massive driving wheels pressing against 2 narrow strips of steel. The physics of what happens when that much force meets a rail is more complex than most people realize. A locomotive doesn't simply sit on track and roll forward. Every rotation of the drivers creates a forward thrust, a lateral force, and a downward compression, all happening simultaneously. The rails absorb this through elastic deformation. They bend slightly, then spring back. This works fine with conventional locomotives. A standard 282 Mikado might generate 50,000 pounds of tractive effort spread across 8 drivers. The rail flexes, recovers, and returns to its original position thousands of times without issue. But the Allegheny wasn't conventional. When its full 7,500 horsepower hit a rail at the exact moment when 770,000 pounds bore down on it, the elastic deformation exceeded what the rail could fully recover from. Each driver carried roughly 96,000 pounds of weight. To put that in perspective, that's equivalent to parking 48 modern sedans on a single point of contact, no larger than a silver dollar. The rail was designed to handle this statically, but not when that weight was simultaneously pushing forward with 67,000 pounds of tractive force. Microscopic shifts became permanent. Do this several times a day, every day, for months, and those microscopic shifts accumulate into something visible, a curve where engineering drawings showed a straight line. The C&O first noticed the phenomenon on their main line through the Allegheny Mountains, the very terrain the locomotive was named after. Surveyors conducting routine track inspections in 1943 found sections of rail that had been laid perfectly straight, now showing deflections of several inches over distances of a few hundred feet. Initially, they suspected foundation settling or frost heave, but the curves appeared only on grades where the Alleghenies ran under maximum load, clawing their way uphill with trainloads of coal. Flat sections remained straight, downhill sections remained straight. Only where the locomotives pushed hardest against the rails did the steel begin to yield. The pattern was too consistent to be coincidental. Track supervisors began keeping detailed logs of where and when the curves appeared. They measured deflection angles, recorded tonnage moved through each section, and correlated the data with locomotive assignments. The evidence was undeniable. Sections where Alleghenies operated under heavy load showed measurable deformation after just 6 months of service. Sections where smaller locomotives ran, or where Alleghenies passed through at low throttle, showed no change. The conclusion was inescapable. The most powerful steam locomotive in regular service was literally too strong for the track it ran on. What made the Allegheny capable of this wasn't just size. Lima Locomotive Works had spent decades refining the science of tractive effort, the actual pulling force a locomotive could deliver at the wheel rim. The Allegheny's 67,000 pounds of starting tractive effort came from a precise combination of boiler pressure, cylinder dimensions, and driver diameter. The boiler operated at 260 pounds per square inch, feeding steam to 2 enormous cylinders, each 22.5 inches in diameter, with a 33-inch stroke. When that steam expanded inside those cylinders, it pushed pistons connected to rods, connected to drivers with a force that could be measured, calculated, and predicted. What couldn't be entirely predicted was what happened to the rails themselves over time. Steel rail in the 1940s was strong, far stronger than the iron rails of the 19th century. The standard section used on main lines weighed 130 to 140 pounds per yard and was manufactured to withstand immense loads. But withstand is a relative term. A rail can handle millions of pounds of static weight. Dynamic loading is different. When the Alleghenies drivers slipped even slightly on a grade, they weren't just pushing, they were hammering. Each slip was a momentary spike of force, far beyond the nominal rating. The rail would compress, the ballast beneath would shift fractionally, and the geometry would change by a measurement so small it couldn't be seen with the naked eye. But locomotives have excellent memory. They return to the exact same spots, day after day, and apply force in the exact same way. The C&O's maintenance crews began documenting the curves. Some were gentle enough that trains could pass over them at full speed without issue. Others required temporary slow orders until the track could be realigned. Realignment meant lifting the rail, resetting the ballast, and spiking everything back down to specification. This worked, but only temporarily. Within weeks, the curve would begin to reappear. The Allegheny was teaching railroad engineers an uncomfortable lesson. There are limits to what infrastructure can handle, even when that infrastructure is made of steel and designed by experts. What's remarkable is that this wasn't a failure of design. The Allegheny performed exactly as intended. It could haul 13,000 tons of coal over mountain grades where other locomotives would stall or need helpers. It reduced the number of locomotives required per train, cut fuel costs per ton-mile, and moved more freight faster than anything that came before it. The bent rails weren't a bug. They were a side effect of pushing thermodynamic efficiency and mechanical advantage to their practical limit. The C&O made a calculated trade: accept some track deformation and budget for extra maintenance, or use multiple smaller locomotives that wouldn't deform the track, but would cost more to operate and maintain. They chose power. The phenomenon wasn't unique to the Allegheny. Other railroads with superpower locomotives reported similar issues. The Norfolk and Western's Y6 class Mallets, the Union Pacific's Big Boys, and the Duluth, Missub, and Iron Range's massive Yellowstones all left their marks on the infrastructure they operated over. But the Allegheny stood out because the C&O ran them harder and more consistently on steep grades where the force concentration was highest. The combination of weight, power, and terrain created a perfect storm for rail deformation. Engineers debated solutions. Heavier rail sections were one option, sections weighing 150 or even 155 pounds per yard. But heavier rail meant higher costs and didn't eliminate the problem, just delayed it. Better ballast was another approach. Instead of crushed stone, some railroads experimented with harder materials that would compress less under load. This helped marginally, but added expense. The real solution was simpler and less satisfying, except that the Allegheny's power came with costs that couldn't be engineered away. The rails would bend, maintenance would be constant. That was the price of moving 13,000-ton trains. The human side of this story often gets overlooked. The engine men who operated the Alleghenies could feel what they were doing to the track. When you're standing in a cab with 260 pounds of steam pressure behind you, and you open the throttle on a 2% grade with a full tonnage train, you're not just controlling a machine. You're managing a conversation between steel and steel. The drivers would bite into the rail, the locomotive would lurch forward, and you could hear the track groan beneath you. Experienced engineers learned to modulate their throttle to avoid excessive wheel slip, not just to maintain traction, but to reduce the hammering effect on the rails. It was a skill that took years to develop. Some crews reported feeling the track shift beneath them on particularly heavy hauls. It wasn't dramatic, no rails buckling or ties failing, but there was a subtle sensation, a slight giving way under maximum force that wasn't present with smaller power. Newer engineers sometimes mistook it for wheel slip and would throttle back unnecessarily. Veterans knew better. They understood they were operating at the absolute edge of what was mechanically possible, and that edge had some flex to it. The trick was staying on the right side of that edge, using every pound of available tractive effort without crossing into destructive territory. The track crews knew it too. They could walk a section of main line and tell you, within a few feet, where the Alleghenies ran under load, the ballast would be more disturbed, the spikes would be looser, and the rail itself would show wear patterns that were distinct from ordinary traffic. Some crews took pride in maintaining Allegheny territory. It was harder work, but it meant they were supporting the most powerful locomotives on the railroad. Others resented it. More work, same pay, and the knowledge that no matter how perfect you made the track today, tomorrow it would start bending again. There was also an economic calculation happening beneath the surface. Every hour, an Allegheny saved by hauling larger trains at higher speeds translated to revenue. The C&O was moving millions of tons of coal from West Virginia mines to the Great Lakes ports. And speed mattered. Customers paid premiums for reliable delivery. Competitors were investing in diesels. The Allegheny represented the C&O's bet that steam could remain competitive if you pushed it to its absolute limit. The bent rails were simply the cost of doing business at that level of intensity. The Allegheny's reign was brief. The last units were built in 1948, and by the late 1950s, diesel-electric locomotives had proven themselves more economical, despite being less powerful per unit. Diesels didn't bend rails because they distributed their power differently. Multiple units could be lashed together to equal or exceed an Allegheny's output, but each unit weighed less and spread its force over more wheels and longer distances. The dynamic loading that caused rail deformation simply didn't occur with the same intensity. When the C&O began retiring the Alleghenies in the late 1950s, something curious happened. Track maintenance costs on former Allegheny routes dropped noticeably. Rails lasted longer before needing replacement. Ballast held its shape better. Curves that had been slowly developing stopped progressing, and in some cases gradually straightened out as the elastic memory of the rail reasserted itself over time. It was as if the railroad itself was healing from years of being pushed beyond its design limits. Today, only 2 Alleghenies survive. One sits at the Henry Ford Museum in Dearborn, Michigan. Another is displayed outdoors at the C&O Railway Heritage Center in Clifton Forge, Virginia, exposed to weather and slowly corroding. Neither will ever run again. The infrastructure they required, heavy rail, robust roadbed, powerful water, and coaling stations, has been dismantled or converted for lighter, faster traffic. The tracks they once bent have long since been replaced, upgraded or abandoned entirely, but their legacy persists in the engineering lessons they taught. The irony is that the Allegheny accomplished exactly what it was designed to do, perhaps too well. Lima Locomotive Works had promised the C&O a locomotive that could move more coal faster than anything else on rails. They delivered that promise. What nobody fully anticipated was that maximizing power and efficiency would expose fundamental limits in the infrastructure that supported it. Other railroads took note. When the Norfolk and Western designed their own superpower locomotives, they built them slightly lighter, with slightly less tractive effort per axle. The Union Pacific's big boys, though larger in overall dimensions, distributed their weight across more driving wheels, reducing the concentration of force at any single point. Modern railroad engineers still reference the Allegheny when designing heavy-haul routes. The limits the C&O discovered in the 1940s are now codified in track design standards. There are formulas for predicting rail fatigue based on axle loading and repetition. There are specifications for ballast depth and roadbed preparation that trace their lineage back to problems the Allegheny exposed. The locomotive that bent rails into curves helped define the boundaries of what's possible when you try to move the maximum amount of weight with the minimum number of machines. There's something almost mythic about a locomotive powerful enough to reshape steel. It speaks to an era when engineers believed genuinely that there were no unsolvable problems, only problems that hadn't been attacked with enough force. The Allegheny was that philosophy made manifest. If the mountain won't move, build something strong enough to bend the earth beneath it. For a few intense years in the 1940s, that approach worked. The coal moved, the railroad profited, and somewhere in the Allegheny Mountains, sections of rail still carry faint curves that weren't drawn on any blueprint, silent testimony to the most powerful steam locomotives ever to turn a wheel in regular service. The question that lingers isn't whether the Allegheny was too powerful. The question is whether we've lost something by building transportation systems that fit neatly within safe, predictable limits. There's efficiency and moderation, yes, but there's also a certain audacity in pushing until the ground itself gives way.